In this video, we'll look at declaring an HDL module and writing a small model. What we need to know about HDL is that it has certain keywords. So the keywords are the language constructs, and HDL has about 100 keywords. So these keywords are predefined by HDL, and we call them identifiers. In the textbook, they're in boldface font, and any good editor will put them in boldface font so it's clear. They'll be able to recognize them and put them boldface so it makes it easier to read your code. They're also always lowercase. HDL is case sensitive, and that's something to remember. And we're talking about Verilog HDL. So a module, that's key. That's the fundamental descriptive unit in Verilog HDL. The term module is enclosed, that closes your module itself. So the keywords module and end module will appear surrounding the text lines of your module code. So the enclosed text, in fact, then describes the circuit. So what we see here in this example, we have module, and then we have end module. We'll do module, and we have end module. And in between those, we do have some code to describe the circuit. But after module, we have what we'll call here is our port list. So it says we have output C and input AB. So this module statement, or this port list, that's our block diagram. So we have A, B, and our output C. That's the block diagram of my underscore and. And internally, it's represented by this amper. That's a logical and. So we basically just have internally to this, we could draw it as a logic gate, an AND gate. So we don't need to do that because there are ANDs described in HDL, but we could define that in this module, in this way with a module. So text between two forward slashes and the end of the line is a comment. So slash slash, that indicates that it's a comment. That's different in different languages, so you need to just remember that. If you want a multi-line comment, you have to do slash asterisk on one line, and then it'll end with asterisk slash. And here shows an example. It says module name my underscore and is a logical and. It has a port list of inputs A, B, and output C. And that after that, it goes ahead and defines, uses this assign statement to do the and it tells us amper is a logical and operator. And then we end our module. We always have a module followed by our end module. Blank spaces are ignored. However, blank spaces can't be, they're not ignored within the text of a keyword, a user specified identifier, an operator, or the representation of a number. Otherwise, blank spaces are ignored. So above, if we look at this block diagram, we have three inputs, A, B, and C. We have outputs D and E. And we can use HDL to implement the block diagram. We could implement the block diagram as a gate level expression at that level of abstraction, or as a Boolean expression. And then it could use whatever gates to implement it. So if we look at this example where this is implementing this block diagram, what we see here, we have our module and our end module to define the module itself. And inside here is where it's defined. And there's an identifier here that names this circuit, so we could use it later, or names this module. So that identifier is alphanumeric, and we can use underscores. We can't use dashes, but we can use underscores. Next to that is the port list. That's the inputs and outputs. So separately, the inputs and outputs have been defined on separate lines. It could be within this port list as well. Then we have another data type here, which is a net data type called a wire. That's W1. So we see W1 up here in the circuit, and that's defined just here as this wire data type. And then we can use it. Then we can refer to it. So and is a gate. So it's one of the predefined gates within HDL. It has and, it has not, and it has or. What we have to know about these predefined keywords is that they also have a port list, and their port list is always outputs followed by inputs. We didn't need to do that here. For our circuit, we have inputs followed by outputs. but for the HDL predefined keywords, these gates have outputs followed by inputs. So we might want to follow that that standard when we create our module port list as well, but we don't have to. But we have to use what's already predefined in HDL. So we have an and, a not, and an or. We see those up here. And we see we've labeled this and G1, we've labeled the not G2, and the or G3. So that's called the instance. This is optional, the instance name, but we use them to help us to show where they are within this circuit that's shown here inside that block. All right, so, and again, key here, we also used W1, that's our wire. A, B, C, D, and E, they were defined in the port list, and then the input and output statements, W1 was defined also as a net list of wire, so we could use it in this, in our code here. And this would then implement, we could take this module, we could compile it, and we could synthesize it, and it would create a circuit something like this. So again, the port list of a module, that's the interface between the module and its environment. It's essentially a block diagram, and we have to distinguish between what are inputs and what are outputs. W1 here is not in the port list. So here we show this, we're trying to implement with HDL the same logic. So we have the same block diagram, so that means we have the same port list. Our port lists are the same, but the level of abstraction is different. Our gate level that we just looked at is using the and, the not, and the or. In this algebra level, we're just assigning, we use this assign statement, another HDL keyword, and we assign D is just equal to A amper B. So that uses it, well, actually, these two circuits are implementing something different, because up here, D, it looks like D is actually what we have up at the top. If we wanted to compare it to this would be D. And this is W1, so we really just have that E is equal to not C. So they're not implementing quite the same thing, but they do have the same port list. All right, so that's our port list. The other thing we should talk about is gate delays that we can show. So the default that we use this apostrophe here, time scale, and it's 1 nanosecond / 100 picoseconds. So the 1 nanosecond, that's a measurement for time delays, and the 100 picoseconds, that's precision of the rounding. So this is the default time unit, and it's used in if we can change that, but that's the default time unit used in the example we're going to show in a moment. But we can change that time scale, and this is used for timing simulations. So if we want to define this propagation delay for the and, or, an inverter, we can do that. We can do that using this hashtag. So hashtag 30. So that's 30 time units, timescale units, which was our default timescale unit, is 1 nanosecond. So that's going to give us the 30 nanoseconds. So 30 nanoseconds for the and, hashtag 10 nanoseconds for the not, and 20 nanoseconds for the or. And again, if our time scale was in milliseconds, this would be 30 milliseconds. So let's take a look at what we'd see here. Now we can measure our timing. So if our inputs initially are 0, then initially we'll end up with our AB is going to be a 0, so W1 is a 0. C naught is a 1, so our D will be a 1, and E will also be a 1. So that's our initial. Then we change our inputs to a 1, and it stays the same. They don't change right upon the change of the inputs. After 10 nanoseconds, well then the output of this inverter changes, so E changes. After 20 nanoseconds, it's going to take another 20 nanoseconds for that to get through to D. So we get no change at 20 nanoseconds. At 30 nanoseconds, now our C prime is going to get through to D. So that's a 0 instead of 1. This is E, that 0 is what ends up going through. We end up with a 0. Even though there's a 1 here, we're still looking at it from 20 nanoseconds ago. So this 0, 0, 0 or 0 gives us this 0 here. And then finally, that when it's 1 or 0, it's not going to change to 1 for another 20 nanoseconds. So it takes a full 50 nanoseconds for these inputs that initially all changed from 0 to 1 for the output of D to become valid. And what did D do? It stayed 1, it went to 0 for 20 nanoseconds, and then it came back to 1. So during this period of time, D is not stable at all. E waits 10 nanoseconds and then becomes stable because it's just dependent upon C. So we can look at that in terms of this table, and you can create a table in HDL as well. And the simulator can also show you a timing diagram. Some simulators will do that for you. Some lower cost ones, sometimes that costs a little bit more. But again, we see our initial change in our inputs. They change here after 10 nanoseconds. Each of these time segments is 10 nanoseconds. Because of this 10 nanosecond delay, we don't get from C to E, right? That takes the 10 nanoseconds till we get that falling edge, and it's an inverter, so it's falling edge. This change here doesn't show up on W1. Well, actually, that W1 change is due to that's due to the AND gates. That's due to A and B, right? So these two cause W1 to change here, and it's this E that causes D to change here, and then this edge is what causes D to become stable again here. So we want to be able to visualize this on a timing diagram and within a table. So again, we can add the propagation delay to the circuits with these hashtags, and we can measure timing. In the next video, we'll look at how we can create a test bench.